first thing I want to do is I want to show you guys one other kind of trick. So oh, that was for a different class. Right, so I've got this length function that we wrote last time, and then I showed you guys how to branch to well, here I changed it to the built-in one, but right, how to branch to use multiple assembly files, and the flush function that remember when we did scanf in C, if you were going to input validate and then if you rejected the input, take more input, you had to first clear the input buffer before you then reprompted for input. So we had to use that flush function to do it. How to interface that, which was written in C, with an assembly program, okay? But then there's sort of the other way that you can do this, which is you can call an assembly program from a C program. The flush thing, what we were doing was calling a C program from an assembly program. So I wanted to show you just one quick example of this. So I've got this length function that I wrote, or that we wrote, right? That all it is it takes a string and then computes the length of it. Okay. So it's equivalent to the string length function that's built into C, but we wrote it. Okay. Let's say that I wanted to call this function from C. How would I do that? Okay. And the answer is that it's actually pretty easy to do it. So let's see, let's go documents, examples. Let's see, what did I call this? Multi-ASM. Okay, we'll just put it there, that's fine. Okay, and I'll call this example.c. Okay, so let's say that I do you know, just something like this, and I define a string, so my string equals, or sorry, car my string of 32 equals what? I don't know. Actually, I'll just leave it. Something like this. Yeah. Okay, and then I could do something like printf the string percent s let's see, so we made this a long integer. So our length function returned in x0, so that's a long integer, has length li \n quote. Okay, what do I need to pass to this thing? Pointer to string, okay, which is what? Just my string, okay? And what's the integer here? Well, good question, right? If I did this the normal way, oops, I could do that, right? So if we do this, okay, and let's compile it real quick and make sure I haven't made any silly typos. All right, so what did I call this? Example.c. Oops. Oh, I forgot a semicolon there, of course. Right? So the string hello world has length 14, and you see how it line broke there? Why did it do that? Yeah, because I put in a new line inside my string, so let me actually get rid of that just for the sake of demonstration. right? So it just prints the string and it prints the length, and it's getting that length from the built-in C function, okay? Which is defined because I included the string.h header, which has the information about where the built-in C library stuff is for handling strings, okay? So strlen here is the built-in function. But let's say that I wanted to use my function that I wrote an assembly there instead. Okay, now it's going to output obviously the exact same number, but this way it'll be using my assembly program rather than the built-in function, okay? So if I want to do that, well, length is an undefined function as of right this instant, right? Okay, so what I need to do is tell the compiler that there's this thing called length that's external to this C file, okay? And the way that I would define that there's a function, I could say, let's see, it'd be car, right? Or the existence of a function would be something like this, right? And then I could define the function down below. But is this function defined within the C file? No. And so what do I need to do? I need to add extern in front of it, okay? And that says that it's an external object, and then the compiler will say, okay, that just means I need to look in a second file, and I know to not find it here, but it's going to be somewhere, okay? And then, of course, the definition here, well, what does our function do? It takes in a pointer to a string, okay, and it accepts it takes in a pointer to a string and it returns a long integer, 64-bit int, right? Okay, now, where is this length function defined? It's defined in this assembly program. Okay, so we've already written it. That's the same as what we've used before, okay? All right, so all I have to do is just add this at the top, and then let's compile it. All right, so to compile it, I've got to do two things. I have to take the assembly, okay, which was length.asm, and output length.o. And then when I GCC, I need to do, what was it, example.c, length.o, output that to, let's say, example, the program, okay? And that's going to compile the C program and also take this object file from when we assembled the length function and kind of link them together, okay? So now, when I run the example function, exact same output, okay? But this time, how was it computing the length instead of before? Yeah, I was using my program that I had written in assembly rather than the built-in C standard function. Okay, so how could this, using sort of a C main and assembly subroutines, be useful in initial code development when you guys are working on stuff? Okay, but you know how to do it in C. The other reason is, let's say that you were working on getting the a length function to work, okay, or some other little piece, and you just wanted to concentrate on that. Well, then you could make sort of a quick little C wrapper to help you test just that little part of it, okay? And then once you get the length part working, then you could work on another part, right? So this could, if depending on how you want to do it, sort of help speed up some of the development or testing or bug fixing, right? Because you can just call an appropriate function within a C program and let C handle some things and assembly handle the other until you get all the other stuff working. And then what do you end up having at the very end? Something that's only an assembly, right? okay, which, you know, is ultimately the goal here, because, well, that's the purpose of the class. Yeah? Okay, so this extern keyword is basically the magic, right? It's like you're putting a placeholder that, hey, there's a function that has this name that takes this stuff in and puts that stuff out, whatever those things might be, okay? And, but it's just not here, it's somewhere else, okay? So that the compiler knows that, hey, it'll be somewhere else and then I'll just sort it out later, okay? See, it's not rocket science, is it? No? Where's Caleb? Huh? He's sleeping? Huh? Oh. All right. So let's see. At Caleb Powell. Unless you're currently buying a sword, then you're about to be fined a GC. So, okay. And it better be a pretty freaking big, nice sword, too, right? So either that or pulling it out of a stone or getting handed to it, or a sword handed to him by an underwater aquatic lady, right? Women in Ponds Distributing Swords 2024. Yeah. Okay. So, yeah, so I thought I'd show you that real quick. That's sort of the complementary half of what we did last time. The next thing is now for something completely different. Okay, so let me actually open up a just a just a blank sort of um, document here. All right. Somebody give me a big number, a really big number. 1 million. Hmm? There is no biggest number. Million's the biggest number? Hmm? No, no, you guys aren't thinking big enough. I mean, huh? 1 to the power of 10 to the 24? That's 1. Hmm. You said to the power of 10 to the 24. But that's not what you said. Okay. 1 times 10 to the 24 is not what you said. You said 1 to the power of 10 to the 24. This equals 1. That, well, it's big. This, yeah, or this. Those are really big. Ah, yeah, the chemistry number. That's the one I was going for. What is it? Yeah, the moles. 6.022 times 10 to the 23rd. Right? So this is Avogadro's, or it's Avogadro, not Avogadro, right? Actually, there's a pretty good XKCD comic as to what would happen if you would have, if you would take a mole of moles, like the animal. It'd be a small planetoid in size. Um, and then they would, of course, all be squeezing together under the gravitational thing. And it'd be hot enough from the compression of all these moles and all the heat that would be released in the process that you know what the surface of this planetoid would be? Probably molten. Huh? That research? Well, research. No, 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 no. This is joke research. XKCD is a comic, a web comic. Okay. And I'm sorry, Cole, but if you don't know what XKCD is, you can't be a computer science major. Like, hand in your geek card right now. Let's. Yeah. Okay. Okay. So big numbers, right? So something like Avogadro's number from chemistry, or like from physics, there's the universal gravitational constant, which is like something times 10 to the minus 11, because gravity is kind of a weak force in a sense. Um, what's the whole purpose of that style of notation, right? So why do I write Avogadro's number as 6.022 times 10 to the 23rd? Why do I write it like that and not 6022 and then just start counting zeros? Because it's a lot of zeros, right? And that's not particularly useful to write out all those crap tons of zeros. What we want to know is sort of roughly how big this thing is in terms of a power of 10, and then the 6.022 part in front says, it's not 2.022, it's 6.022, okay? Okay, and we're all cool with scientific notation, right? Because we've all, well, most of us have graduated high school. Few of you not yet, but y'all are cool with scientific notation, I would hope, right? I mean, this is also not rocket science. Okay, so what are the conventions with scientific notation? Would I ever write the following? Oops. Could I write that? Is that the same number? Yeah, same number, but would I ever actually write it that way? Only in one circumstance, and that's if I was doing arithmetic with multiple numbers that were expressed in scientific notation. Okay, but if I was just writing the number down by itself, I would never actually write it that way. Okay, nor would I write it as 60.22 times 10 to the 22nd. Still mathematically equivalent, but I would never actually do that in the scientific notation um, convention. Okay, so what is the scientific notation convention about how many things go immediately before the decimal point? Precisely one digit, and that digit is never zero. Okay, because if it were zero, that'd be like the case of 0.6022, right? Okay, so the digit that's immediately before the decimal point, there shall be one and precisely one of those, and that digit shall not be a zero. It must be non-zero, okay? Then the stuff that follows the decimal point, well, that's really up to you, okay? Or maybe better put, it would be up to. Okay, so this is one of the luxuries about being a mathematician. What do we don't have to care about that scientists do when it comes to measuring things? Units and also uncertainty, okay, and error and all of that, right? Because our numbers are all just made up anyway, so who cares? Okay, but so like if you did 6.02 times 10 to the 23rd, like, yeah, maybe you could go out a few more decimal points there, but like, do we really care for government work here? No. Okay. So the stuff that follows the decimal point, right, is kind of just depends on measurement uncertainty and all of those things. But for our purposes here, let's just, 0.022, whatever. I might as well have pulled it out of thin air. Okay. The other thing that we have to do is we need to record the exponent. Okay. So if I told you that the stuff that followed the decimal point was 0.022, the stuff that was before the decimal point was a 6, and the exponent was a 24, did I actually have to write down the 10? Not really, okay, because, like, what other base would you use besides 10 in the scientific world? Well, yeah, but how many times have you run into something expressed in scientific notation as like 6.022 times e to the something? Yeah, exactly. Like we never express numbers that way. Now, yeah, functions, you may take natural logarithms all day long or whatever, but in terms of just the number itself, it's never a power of e. It's always a power of 10, okay? And so the 10 there doesn't actually need to be explicitly specified because you just know that from context, right? Okay, so what I have to tell you is the thing before the decimal point, the stuff after the decimal point, and the power, right? And the 10 part is always the same. Okay, now let's change over and let's say that we are doing this in binary, okay, rather than base 10. Okay, so what changes is that the 10 will now be a 2, right? So let me just take, for sake of example, a simpler number like 1.5, okay? And let me do, say, 2 to the 0, just as a quick initial example. Okay, first off, we'll all accept that that's a valid number. What's the digit, or the bit, excuse me? Well, okay, sorry. I'm writing it there, 1.5. How really should I write this? Really should write it like that, okay? What's the difference here? 1.1, okay, if the place value in binary are powers of 2, then you've got the 1's place, the 2's place, the 4's place, and so on. What is, excuse me, what is it to the right of the decimal point of the radix? It's halves place, quarters place, eighths place, 16th place, and so on. Okay, and how did I get that? Hey, I was wondering, yeah. Okay, so halves place, quarters place, 16th place, and so, you know, all of those guys, right? So just like the place values in base 10 are powers of 10, in base 2, they're powers of 2. And those powers could be negative, which is what they are to the right-hand side of the radix. Okay, now I say radix here because what do I really mean? It's like the binary version of the decimal point. But can you have a decimal point if you're not doing things in decimal arithmetic? It's, you can't, it'd be silly to call it a decimal point if there's no base 10 anymore, right? So the general word we'll use is radix, R-A-D-I-X. Okay? Huh? Bicimal? Okay, Cole suggests we call it the bicimal. I suggest we call it the radix. Which one do you guys think is better? And Chad, Steezy, you don't get to answer. And nor did Caleb. Oh, but he's not here. Okay, and he's not buying a sword, so. Yeah, okay. But yeah, we'd have to come up with a different name for it. And the radix is the conventional word here for the general the concept of like a decimal point, but that doesn't matter what base. So it's sort of base agnostic. Okay. And the word there, by the way, is Latin. It means root. And if you're kind of thinking like, gee, that looks like a whole lot like the word radish. Yeah, because what kind of vegetable is a radish? It's a root vegetable. Okay. Yeah. That brings us to, have I ever told you guys my favorite ancient Greek word? I'm not. So it is Raphanidao. Raphanidao. So, hey, Raphanis. Is the word for a radish in Greek. Okay, so Raphanidao is a verb that literally means to radish. I'll leave it up to your imagination to what happens with that radish. I have told you this, yes. It was a punishment for infidelity. The radish would be thrusted up the fundament, as the stuffy Victorian dictionary says. Yes, it was in punishment for infidelity, and this happened to in Aristophanes' Clouds. Right Logic, who is sort of a character lampooning Socrates, and Wrong Logic, who is a character that's lampooning the sophists, get in an argument, and the merits of their arguments are judged by placing two male chickens upon scales to see which one is bigger. And I don't mean the actual birds, okay? Right Logic loses, even though his argument was better, and is radished by the loser. Yeah, so it's sort of ancient Greek toilet humor at its finest. Okay, yeah. All right, anyway, so there's your liberal arts moment of the day. So really I should write this as 1.1 times 2 to the 0. Okay, thinking in binary. So what was the convention about the, how many things need to go immediately before the radix? One thing. There it is. Okay, and what must that thing be? Not a 0. Okay, well, if it's not a 0, what does it have to be? Because we're fresh out of bits, right? There is only 0 and 1, and if it's not 0, it therefore must be 1. Okay, now that's a difference between the base 10 system, because if I tell you that the initial digit is not a 0, is that enough for you to know what the initial digit is? No, because it could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. You don't know which one, right? So I have to specify. However, here, if it's in binary and it's not a 0, it must be a 1. So do I have to tell you that initial 1? No, I get that bit for free. Okay, and which is kind of nice. Okay, so what I'm going to do here, let's take this number. The Mantissa okay, here it's a 1, the stuff after the radix. I don't need to specify and I do need to specify that the exponent is 0. Okay? All right, now if we're going to do like everything that we're doing or up there that's on the page is just kind of more math style, like math class, right? I've never actually encoded any of this for the purposes of storing it on a computer. That's the next part, okay? All right, so are we clear here that the stuff after the radix is a 1, okay? The exponent needs to have a value of 0, and I don't need to specify the one that's before the radix, okay? There's one other thing, though, that I really should specify, okay? And what is it? And I should have done this, too, with Avogadro's number. But by not specifying it, the assumption was that it was a certain thing. Not the base, that's the 10. I'm sorry? I can't hear you. Oh, the dot. Yeah, no, not that either. Yeah, exactly. The number could be negative also. Okay, and positive or negative, right, in math, we signify obviously with a symbol. And if there is no symbol for either plus or minus, the assumption is that the number's positive, okay? And it's only if you see the minus sign explicitly written that the number is negative, okay? But if I were to encode this in a binary sense, I need to spend 1 bit to do that, right? In the same way that when we were dealing with integers, right, we needed to use a bit that indicated whether or not the number was positive or negative. Okay, so what's the convention? If the number is positive, then the sign bit is 0. Okay, if the number is negative, we'll make this sign bit a 1. Okay, that's just the convention. You could have just as easily flipped it around and said we'll make 1 positive and 0 negative, but that's not the convention. Okay, and I think the reason it's not the convention in floating point is because how did we deal with positives and negatives as integers? Okay, what was always true for positive numbers? Well, they had that first bit was a 0. Okay, but how did you take a positive number and negate it? What do you do to its binary representation? Yeah, you do the 2's complement, okay, which makes the far left bit a 1. Okay, so it would be kind of nice if the pattern was the same with integers and floating point, right? That's just kind of convenient, I would think. Okay, so I need to also specify the sign, okay? Okay, so the convention is a sign bit of 0. Okay, now, if I'm going to store this on a computer, how many bits do we want to use for it? Well, that's kind of up to us to some extent, but also not up to us to some extent because we're not also making up our own computer. We have computers somebody else has already designed, okay? And what would make sense then? How many bits should we spend on this? Well, how many bits have we spent on integers? Either 32 or 64. Yeah? Okay, so those are the 2 standards we'll look at is the 32-bit and the 64-bit versions. Okay, so let me start with 32 bits. Okay, we have 32 bits to spend. Okay? Well, we definitely have to spend 1 on a sign bit. Okay, so that leaves 31 left. Okay? So what are the 2 things that I still need to specify or store? I need to store the stuff that comes after the radix, okay, which is called the Mantissa. And I also need to store the exponent. Okay, now in this example, the exponent's value is 0, and I'll explain in a minute why I keep saying the word value. And the radix is a 1, followed by, of course, as many zeros as we need to. Okay, because is 6.00 the same as 6.0 mathematically? Yeah. Okay, but if I'm going to say I have to use a specific number of bits for the Mantissa, then anything that I don't already have will just be, of course, zeroed out, right? I'll pad it with as many zeros as needed in order to fit it all where it should be. Okay? All right, so then the question is, well, we've got 31 bits left. How many should we spend on the exponent and how many should we spend on the Mantissa? Got to make a choice, right? And the convention for this is 8 bits for the exponent, and that leaves therefore 23 bits for the Mantissa. Okay, so in a sense, we only encode 32 bits, but we get 33 bits worth of information out of it because what was the thing that was immediately before the radix? Must be a 1. I don't have to encode it, but I know it's there, right? So this is why I say we get 1 for the price of, or 2 for the price of 1. Okay, it's like a, Black Friday sale at Kohl's. You know, how many of you guys are going to go do Black Friday stuff next week? What's on your wish list for Black Friday? Nothing in particular. Anybody on the hunt for a PlayStation or an Xbox? You might take your shotgun with you if you are, because you may need it, right? Yeah. So is Black Friday a thing in, no? Is what? What? I can't hear you. It means riots back home? Well, that's not too far off. I mean, some of the videos I've seen from people fighting over, junk at Walmart is, yeah. Now, I stay as far away from possible from retail establishments on that day. Huh? What, to watch the train wreck? Well, I don't know. It's sort of also therefore this year and last year, COVID super spreader events. Mm. Yeah, it's going to be a bloodbath this year. So, anyway. Yeah, because you can do it from your couch, right? I'm with you on that, Cole. Okay. All right. So this is the convention, right? The other convention is what order do we put these things in? And the convention is we put the sign bit at the far left, okay? Then we have 8 for the exponent, and then 8, 12, 16, 20, 23. Okay, so sign bit, exponent, mantissa. Okay, that's the order we put them in. Okay, so let's take my example here of the number 1.5. Okay, and I'm going to pop open a web browser because you guys are going to love this. Okay, float toy. Well, if you Google that, you'll get all kinds of inflatable whatevers, right? But in particular, you also get this really handy dandy website, okay? Written by a guy named Evan something or other, Evan W. So let's take the number 1.5, okay? Now, what did we say? Well, if I wrote this sort of as a binary style scientific notation, it'd be 1.5 times 2 to the 0, okay, times 1 because it's a positive number, not negative 1, right? Okay, so is that okay? Now, what did we say that the mantissa was? Just a 1, right? And then we need to put 22 more zeros because just to fit it where it needs to go. Okay, so do you guys accept that the red part, which is the mantissa part, is a 1 followed by a crap ton of zeros to fill it up? Yeah? Sound good? You guys also accept that the sign bit is a 0. That's the blue bit. Okay? And now we come to the annoying part. Let's look at the green bits. That's the exponent. What is the exponent in our sort of scientific style notation? 0. What do we have in the green bits? That sure as heck does not look like 0. So what the hell is going on there? Okay, those of you who've taken CS 101, what's the distance? What's the thing here? Yes, Owen. The exponent bias, which I haven't mentioned until this moment. Okay, so the exponents are biased by a fixed amount, and that fixed amount is different depending on how many bits you're using. Okay, so for 32 bits, the bias is fixed, it's 127. So the exponent looks 127 bigger than it actually is. Okay, now look at those 8 bits. What value are recorded by those 8 bits? A 0 followed by all ones. Do you guys accept that that represents 127 as an unsigned number? Yes. Take 127 away from it, what do you get? 0, which is what it was supposed to be. Okay, so the exponents look bigger than they are. Now, this begs the question, WTF? Okay, you agree? Why on earth would you do this? Okay, there's a very good reason for it, and it's kind of a historical reason. Do you guys agree that we need to be able to encode both positive and negative exponents?
No.
You do not agree?
No, I do.
You do agree. Okay. We need to be able to encode positive and negative exponents. Positive exponents would be associated with really big numbers, and negative exponents would be associated with really tiny or precise numbers. Okay? And both are important, right? For every Avogadro's number, there's a Newton's universal gravitational constant, right? Which, like I said, is like something times 10 to the minus 11, right? Well, there the precision is really important, huh? 6.67 times 10 to the minus 11 is the universal gravitational constant. Thank you, Fard. Okay, so, yeah, I think that earns you a gentleman coin, right? Huh? What do you mean it's going to my head? The gentleman coin thing?
Yeah.
No, it's okay. I don't know. Maybe I should take a gentleman coin away because he forgot the sig figs or the uncertainty. I'm kidding, Farton. Okay, yeah.
Did you consult the about us section about how you can earn GC before you handed it out?
No. The,
It's a free pass.
yeah. Okay. Anyway, so Marilyn, we don't have it on the server, but I'm sure we can create Ladycoin, and I'm sure that there's an exchange rate of 1 to 1. So don't worry. Right? If you want to hop on the Discord server too with the boys, you're welcome to. Okay. Yeah. Okay. So anyway, the exponent looks bigger than it actually is. So we need to be able to use negative exponents, okay? But for historical reasons, and we'll talk a smidge more about this, if I wanted to have both positive and negative exponents, then I would need to store that exponent in 2's complement, okay? Or some sort of system that allows me to have both positives and negatives. Okay, we store it basically as an unsigned number rather than a signed number. And of course, the difference between those is 127 when you are dealing with 8 bits, okay? And the historical reason for this is because if the exponents for all the numbers are unsigned, it makes it much easier to determine who has a bigger exponent than somebody else, okay? Whereas if the numbers are in signed or 2's complement, that process is more difficult, okay? And the reason you need to be able to compare the exponents of 2 numbers is to determine how to do arithmetic, okay? So let me do an example here on the board. Let's say that I wanted to add 6.1 times 10 to the second and 9.8 times 10 to the third. Okay, if I want to add those 2 numbers, okay, then what's the problem with their exponents? They're different, okay? So I can't just do whatever 6.1 times plus 9.8 is and then write it that sum plus or times 10 to the whatever. Okay, so what I have to do is I have to look at this and say, all right, I'm going to have to deliberately change the exponent of one of these numbers so it matches the exponent of the other number. All right, well, that gives me a choice. Which one should I change? Should I change this guy that has an exponent of 3 to then have an exponent of 2? Or should I change the one that has an exponent of 2 to have an exponent of 3? Which one? Owen? The one that has the smaller exponent. Why?
Why not?
Okay, why is that the choice? okay? There's an even better way to put that. Which one is going to involve less loss of precision potentially? Changing the first one, the smaller number, right? So would you, if I had the number pi, okay, and I wrote pi as 3.1, am I worse off if I write pi as 3.0 or if I write it as 0.1? Right? So if I drop one, if I lose one of those digits, would I rather lose the 3 or the 1? I'd much rather lose the 1 because that's the least significant. 3 is more significant. Okay, so the convention then is we will denormalize, which means change we will change the smaller number to and deliberately break our convention of always putting a non-zero thing before the radix. Okay, by doing so, I can now add them because their exponents match. So I can do 9.8 plus 0.61 times 10 to the third, right? Essentially just factor out the 10 to the third, okay? And then what's 9.8 plus 0.61? 10.41. Okay, and that gives me my answer. Okay, however, obviously what's wrong with this answer? Right, it violates our rule, so I have to renormalize the answer by fourth, I'm sorry. Arithmetic is hard. Okay, yeah, so I have to renormalize the answer to make the exponents, it obey the rule, okay, once I'm finished with all the arithmetic. So the rules go out the window for the arithmetic purposes part, but they come back into the window when we want to write down the answer in our proper form. Okay, so let's just say, for whatever reason, that, now this example, like I said, is completely contrived, right? I just made up those two numbers. But if I was doing something in science, right, maybe there's an uncertainty to both numbers, okay? And there are, of course, rules as to how you sort of compound that uncertainty when you add two numbers together, okay? It's annoying, but that's what you get if you become a science major, okay? You reap what you sow. Okay, so the reason that we store our exponents in binary as unsigned is because it makes it a lot easier to just instantly know which exponent is bigger than which exponent. If they were signed, that wouldn't be as easy. Okay, so that's the historical reason that there's this offset. Okay, is that all right? Yeah? Okay, so how do you compute what the offset is? How many bits did we use for the exponent here in the 32-bit version? 8. Take 1 away from that. What's 2 to the 7th? 128. Take 1 away from that. Okay, so it's 2 to the number of bits minus 1 is how you get the bias from the number of bits. Okay, yeah, and that pattern actually continues. Okay, so for our 32-bit number here, our green bits look